It is perhaps the most ubiquitous tool in human history. A simple cylinder of wood and mineral that has drafted the blueprints of skyscrapers, sketched the masterpieces of the Renaissance, and scribbled the notes of everyday life. But don't let its humble appearance fool you. To create a modern pencil, engineering must bridge the gap between geology and high-precision manufacturing. Hidden beneath that yellow paint is a complex composite material, a fusion of graphite and clay that must be engineered to thicknesses of less than 2 millimeters while maintaining the strength to withstand the pressure of a human hand. In this deep dive, we are deconstructing the pencil. We will explore how raw carbon, mined from the earth, is transformed through intense heat and hydraulic pressure into a precision instrument. This is not just a stick of wood. It is a marvel of material science, where the friction of a single stroke creates a layer of atoms only nanometers thick. Welcome to the engineering chronicle of the Graphite-Clay Fusion. Every pencil begins deep underground. The primary ingredient is graphite, a crystalline form of carbon. On a molecular level, graphite is arranged in stacked sheets, allowing layers to slip off easily onto paper. However, pure graphite is too soft and greasy to function alone. To give the pencil its hardness and durability, engineers introduce a second critical material, kaolin clay. This fine white silicate mineral acts as the binding matrix. The ratio between these two materials is the secret formula for every pencil grade. A higher concentration of graphite produces a B or soft lead, resulting in dark, smudgy lines, while more clay creates an H or hard lead, perfect for technical drafting. These raw materials are pulverized into a microscopic dust, with particles measuring only a few micrometers across. This ensures a smooth, scratch-free writing experience. The journey from raw earth to precise writing core begins in the massive mixing vats, where water is added to create a heavy, slate-colored slurry. Consistency is the enemy of friction. To ensure the pencil doesn't catch or drag, the graphite and clay mixture must be homogenized at a molecular level. This occurs in a process called wet grinding. The slurry is pumped into huge rotating mills filled with steel balls. These mills spin for hours, pulverizing any remaining grit until the mixture is as smooth as silk. Once the desired consistency is achieved, the water must be removed. The mixture is pressed into large flat cakes, which are then dried and crushed again into a fine powder. But this isn't the final form. To create the lead, the powder is mixed with a small amount of water to create a dough-like substance with the consistency of modeling clay. This dough is the raw material for the extrusion phase, where the pencil's core finally begins to take its iconic cylindrical shape. Precision sensors monitor the moisture content at every second, because even a 1% deviation can cause the lead to snap during the manufacturing process later on. The graphite dough now enters the extrusion press. Under immense hydraulic pressure, exceeding several thousand pounds per square inch, the paste is forced through a tiny, precision-drilled sapphire or diamond die. What emerges is a continuous, wet thread of graphite, looking very much like gray spaghetti. This thread is incredibly fragile at this stage. It is automatically cut into lengths called leads, typically about 7 inches long. These leads are then straightened and air-dried on moving conveyor belts. However, they are still far too soft to write with. They lack the structural integrity to survive the sharpening process. To transform this brittle clay-carbon mix into a rock-hard writing tool, we must harness the power of extreme thermal energy. The leads are packed into sealed crucibles, prepared for a journey through the heart of a furnace that mimics the conditions found deep within the Earth's crust. Inside the kiln, the temperature climbs to a staggering 1,800 degrees Fahrenheit, or approximately 1,000 degrees Celsius. This is the sintering process. As the heat intensifies, the kaolin clay particles undergo a chemical transformation, fusing together to form a hard ceramic latticework. This matrix traps the graphite flakes in a rigid structure. Without this step, your pencil lead would simply crumble under the slightest pressure. The timing must be perfect. If the leads are fired for too long, they become brittle. Too short, and they remain soft and useless. After several hours in the white-hot heat, the leads are slowly cooled. They emerge as hard, metallic-looking rods. But there is one final chemical treatment required. To make the pencil write smoothly, the porous ceramic structure must be filled. The leads are submerged in a bath of hot wax and fats, which soak into the microscopic pores of the lead, acting as a lubricant that allows the pencil to glide across the paper with zero resistance. While the core is being forged, the armor is being prepared. Most high-quality pencils use incense cedar, a wood prized for its straight grain and lack of knots. This makes it perfect for sharpening without splintering. The wood arrives at the factory as slats, thin rectangular blocks about half the thickness of a pencil. A high-speed milling machine, or groover, carves 8 narrow semicircular channels into each slat. These grooves are cut with tolerances of less than a hair's width. Each groove must be perfectly centered to ensure the lead sits in the exact middle of the finished pencil. If the lead is even slightly off-center, the pencil will be impossible to sharpen properly, as the wood will support one side of the lead more than the other. The slots are treated with a light wax and stained to give them that classic reddish-brown hue, preparing them for the most critical assembly step, the sandwich. Precision gluing is the secret to a pencil that doesn't break. An automated dispenser applies a thin, even layer of high-strength PVA glue into the grooves of the bottom slat. Then, a mechanical lead layer drops the fired graphite cores into the channels with lightning speed. Immediately after, a second grooved slat, the top of the sandwich, is placed over the leads. This graphite-wood sandwich is then placed under a massive hydraulic press. It stays there for several hours as the glue cures. This creates a solid composite block. The bond between the wood and the lead is so strong that they essentially become a single unit. This structural integrity is what allows a pencil to be dropped without the lead inside shattering into a dozen pieces. Once dried, these slabs move to the shaping station, where they will finally take their individual forms. Now, the solid slabs encounter the shaper. This machine features 2 sets of high-speed steel cutters spinning at over 10,000 revolutions per minute. The top cutter carves the top half of the pencils, while the bottom cutter carves the lower half. In a single pass, the slab is transformed into 8 individual pencils. Most pencils are carved into a hexagonal shape. This isn't just for aesthetics, it serves a functional purpose. The flat sides prevent the pencil from rolling off a slanted drafting table, and the angles provide a superior grip for the human hand. For younger students, pencils are often left round to be more comfortable for small fingers. As the pencils emerge from the shaper, they are individual units for the first time, but they are still raw wood. They require their iconic finish to protect the cedar and signify the brand. The finishing process is an exercise in speed and repetition. The pencils are passed through a series of lacquer baths. A typical high-quality pencil receives between 5 and 8 coats of paint. This thick layer of lacquer seals the wood, preventing it from absorbing moisture and warping. After the paint is dried and buffed to a mirror finish, the branding is stamped using gold or silver foil. Finally, we reach the ferrule, that small metal band at the end. It is usually made of aluminum or brass. A machine slides the ferrule onto the end of the pencil and crimps it, biting into the wood to ensure a permanent hold. A small plug of synthetic rubber, the eraser, is then inserted into the ferrule and squeezed tight. The pencil is now complete. A precision-engineered tool made from minerals, clay, wood, and metal, ready to record history. Before a pencil reaches your desk, it must prove its worth. In the quality control lab, random samples are subjected to the point strength test. A mechanical arm applies increasing pressure to the tip until it snaps, ensuring the lead meets the required break strength standards. Another machine performs a wear test, scribbling miles of lines to calculate how many feet of writing a single pencil can produce. On average, a standard HB pencil can draw a line 35 miles long. Engineers also check for light fastness and smudge resistance. Every batch is verified for lead centering and wood quality. Only after passing these rigorous stress tests are the pencils sharpened and packed. From the deep graphite mines to the precision kilns and high-speed shapers, the journey of the pencil is a testament to the idea that even the simplest tools require the most complex engineering. The next time you pick one up, remember, you're holding a masterpiece of material science. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.